series, and it's a great end to the session and the day to have him tell us about that. Yeah.
Great. So thank you, Vedika, for this nice introduction. Yeah. So it's my pleasure to be here in this marvelous city and to be talking to many colleagues in the field of quantum simulation. So the work that I do in my group is basically focused on quantum simulating far from equilibrium dynamics of gauge theories on state-of-the-art hardware. So we've done a whole bunch of works on gauge theories. I'm sure Zohre and Nicholas gave you a good introduction on gauge theories, so I don't have to do that. Today, I will focus on one of these works, which is the observation of disorder-free localization on a quantum processor, where we actually probed this phenomenon on in a 2+1D lattice gauge theory, so 2 spatial dimensions and 1 temporal dimension. Good. So this is the paper that I will talk about. We did it in collaboration with Pedram Rushan's team in Google Quantum AI. So let me pay homage to my co-authors. So from Google Quantum AI, there was Pedram and Elliot, and also Yuri Lenski as the senior guys. But Yuri, I couldn't find a photo of him. There's also Ghadaghish Musna from the Max Planck Institute for the Physics of Complex Systems in Dresden. And you also see Dima Kovrigin and Johannes Knolle from Paris and Munich, respectively. OK, so let's get to business. Basically, let's talk about localization or lack thereof. So if we consider what we know from textbooks, if we consider a non-interacting system of free electrons, basically your single particle wave function is a Bloch wave. And you can find the electron anywhere in the lattice. There's a probability of finding it anywhere in the lattice. So the dynamics is completely delocalized. However, thanks to Anderson, we know that if you add any kind of disorder in 1 and 2 spatial dimensions, you right away localize. Your single particle wave function is an exponential decay in distance. And basically, there's no transport. If you go to 3 spatial dimensions, you get a kind of phase transition at a finite critical value of the disorder. But in this talk, we're going to focus on 1 and 2 spatial dimensions. Well, actually, let's just focus on 1 spatial dimension right now and add interactions. And this brings about the interesting phenomenon of many-body localization, right? So the general wisdom right now is if you have interactions at a given strength of the interaction, there's a critical value of the disorder strength above which you localize, at least for very large timescales, even in the thermodynamic limit, right? There's actually an ongoing war right now whether MBL is a stable thermodynamic phase. But we don't care about that so much in this talk because we're looking at finite timescales, albeit very long timescales. And you see that you can, as you will see, one can distinguish between localized and delocalized dynamics within these timescales. But now the question arises, is there a way where we can find localization in a system without by hand adding disorder over space? And the answer is yes. And this phenomenon is colloquially known as disorder-free localization. And it was first shown or demonstrated by the following authors, Smith, Knolle, Kovrigin, and Musna, already 8 years ago. But until our experiment, it was not experimentally realized. And that's what we will discuss today. So to put things on a formal footing, let us consider the following Hamiltonian, which actually describes a Z2 lattice gauge theory. So here I describe a single chain, but we will also go to 2 spatial dimensions later. And actually, our formalism is general to any spatial dimension. So here, unfortunately, there's no pointer, but basically the green observables or the green operators denote gauge fields. And you see they are denoted by diamonds on this ring, which is basically a chain with periodic boundary conditions. These are so-called gauge degrees of freedom. And we will discuss a little bit what that is in case you didn't pay attention in Zohre's and Nicholas's talks. And also the blue degrees of freedom are matter qubits, and they're denoted by circles. So the 3-body term that you see over there, sigma z, z, sigma z, basically entails, you can think of it as particles either tunneling between neighboring sites or pairs of these particles being created or annihilated. And the job of the Z term in the middle, this qubit Z, it's a gauge field. What it does is it acts on the electric field denoted by X, such that Gauss's law is maintained, such that this local Z2 symmetry is maintained. And the way you think about it intuitively is through Gauss's law from classical electrodynamics, right? If you move an electron and a positron, the electric field between them has to move such that it's always pointing from the positron to the electron so that you don't violate Gauss's law. And the first term that you see, sigma x, this is basically the matter occupation, and mu denotes the mass. If you look at the circuit on the left-hand side, you see that basically we implement a Floquet cycle of this Hamiltonian. So the two C0 gates, the RZ rotation gate, and the two C0 gates following it implement the three-body term. And then you have the X rotations for mu and H. So again, what we do is we prepare two initial states that are they are very much disorder-free and almost fully translation invariant. So you see that we align the matter fields in either plus X or plus Z, depending if you're looking at the single sector or super selection state, and I will explain what these terms mean. And then I align the electric field on the links between these sites in such a way along between the X and Y axis at an angle between them, everywhere in the same direction except in the middle. I rotate by 180 degrees. The reason I do this is just like in the Anderson localization case, I want to create an energy bump and see if it spreads in the system or not. In the case of Anderson localization, it does not, but let's see what happens here. So here, the chain is 38 qubits, 19 matter qubits, and 19 gauge qubits. And these are the results. So in the single sector case, you see that this energy bump that I created very quickly dissipates. So here I'm looking at local observables. I'm looking at the matter occupation, the electric field, the three-body term, and also the local energy density. And you see that it very quickly dissipates and spreads throughout the whole system. So you can say the system is delocalizing or thermalizing here. On the other hand, the case of the superposition initial state, you see that this energy bump is very well localized up to the considerably long times that we are able to access on the quantum simulator. And here one can say that we are in a localized regime, at least over the time scales that we can access experimentally. So now you can ask me, where did you hide the disorder here? I mean, usually disorder is connected with localization, so what's going on? And what I can tell you is to consider the following Hamiltonian that you have here. As I will show you in a little bit, the gauge theory that I showed you on the previous slide maps exactly onto this model. You see this GJ eigenvalues. These are the eigenvalues of the generator of your local Z2 symmetry. And it can take only two values. Remember, it's a Z2 gauge symmetry. And these are plus or minus 1. So the first term is just counting the number of Z operators that you see on the links between the vertices. The middle term counts the X operators, which are the electric fields. And then the four-body term that you see at the very right, this arises from Gauss's law. So now what we can do is we can get rid of the disorder to make things, again, disorder-free by introducing ancilla qubits at the vertices where the matter was. So basically, I integrated out the matter using Gauss's law. And instead of the matter, I put ancilla qubits, which actually commute with your Hamiltonian. So they're conserved operators. They're conserved quantities. And this is the concept of quantum parallelism. So instead of really sampling over different disorder configurations, what I can do is I can go in a superposition of the two eigenvalues of sigma x. So basically, I can align my spin, my sigma x spin along the z direction, and I automatically sample over all possible disorder configurations. So here we have to pay homage to the initial work on quantum parallelism by Paredes et al. I cite the paper there, and they did it for cold atoms, but here we show how one can do it for digital processors, and we actually implement it experimentally, as you will see in a bit. And the mapping that I told you about, how you go from the Z2 lattice gauge theory to this spin model, is as you see on the screen. So we have the local generator, Gj. It takes the following form. And its eigenvalue, Gj, can be either plus or minus 1. But I can write my sigma x operator, the matter operator, exactly in terms of the third term that you see on top of the screen. OK. So now, let us talk about what single sector and super selection means. So when I talk about sectors, I mean a set of values of these background charges, Gj, over the entire lattice. One sector, a set of these values defines one sector, and these sectors are decoupled from each other because of your local Z2 symmetry. If I set my ancilla qubit sigma x to +1 everywhere, this in principle means that I have a clean system. There's no disorder in it. But if I set sigma x randomly over the lattice, so +1, +1, -1, -1, -1, whatever, then I have a disorder configuration. On the other hand, if I set sigma z to 1, as I mentioned earlier, then you have a simultaneous equal superposition over all these super selection sectors. Now let's look a bit more schematically at what these super selections are. As I mentioned, they're decoupled. Some of them are ordered, but there's an exponential number of them that is disordered, as you see here. Now, the benefit of using these ancilla qubits and the concept of quantum parallelism is it avoids falling into certain pits or pitfalls that now are the root of heated debates in MBL, whether MBL exists or not. So there are certain things called rare events. The technical name is thermal inclusions. So the way you think about it is as follows. You have a very disordered lattice, but sometimes you may go into certain regions of the lattice where the disorder is quite weak. So you get an island on your lattice that is quite thermal. And what this does, it leads to something called the Griffiths effect, where basically this thermal region starts entangling distant localized regions together. And so if you are close to the MBL transition, this may actually lead to thermalization, even if you are on the side of the MBL phase. And the question arises if this really completely destabilizes MBL. So in our case, by using quantum parallelism, we actually take these rare events automatically into account. So that's another advantage of the work we do here. So now let's look at the preview video that I showed you in my slide. And this is the same physics, but in two spatial dimensions. So what I do in the top left link, so here the diamonds are links, and the small circles that you see are matter sites. And we have 81 qubits, yeah? 39 matter qubits and 42 gauge qubits. I prepare the energy bump in the top left corner, and I just let it spread. As you see, there's a marked difference between the single sector and the superposition cases. So the single sector case, which should be delocalized, shows that this bump very quickly spreads over the entire lattice. While the superposition case shows that this bump is pretty much localized throughout the entirety of the experimental timescales. But you know, heat maps can be a bit deceptive, so let's look at cuts. So here again, I'm showing you these cuts. And the circuit is at the bottom, so I don't want to go into too much detail here. But if you look at the spread of the energy in each of these qubits, so you see we have the red curve at the lower right. And the red curve is where I prepared this initial energy bump. You see that it very quickly in the single sector case goes along with the gray curves. So indicating delocalization starts behaving like them. On the other hand, in the case of the super selection sector, you see that your dynamics is actually quite slow. Yeah, OK, you can argue that at late times, it's also behaving like the rest of the system. And we're not denying this. We're not claiming that this is clear MBL here. All we are seeing is that you see marked difference between both cases. And your dynamics is significantly slower in the case of the super selection case. Good. So now, let me also talk about some entanglement entropy measurements that we did, in particular, rank 2 Rényi entropy. And the interesting bit about this is it shows you how you can probe nonlinear behavior when you start in a superposition case, in the superposition initial state, that you cannot do by disorder averaging. So basically, what I showed you earlier, these local observables, they're all linear in system size. But actually, there are certain nonlinear observables that basically you cannot do disorder averaging on them, and Rényi entropy is one of them. And indeed, what I show you here on the top, if you look at the top row, on the left-hand side, you see the growth of Rényi entropy over time for different subsystem sizes of a chain that has 8 matter qubits and 8 gauge qubits. What you see is that it's markedly different than if you do disorder averaging, which we show on the right-hand side. We also show the growth of this Rényi entropy in the uniform case, in the bottom left, and we also show it for a given subsystem size, how it grows for all 3 cases over time. And the difference that you see here between the top 2 panels is that you have, let me say, intersector interference that you can see in the case of the superposition, but that by default you cannot see it in the case where you disorder average. And yeah, this we will skip due to lack of time. And here I want to talk a little bit about classical simulability. So what we did in MPS, or in tensor networks, we considered different system sizes, 4x4, 6x6, and 8x8. Yeah? So now when I say L, that means it's either 4, 6, or 8. And we looked at various observables here. And what you see is the exponential growth in the bond dimension in MPS over time and with, in system size. So as you can see, we considered these different square lattices, 4, 6, and 8 on each side in terms of the matter qubits, the number of matter qubits. And as you can see, the bond dimension grows exponentially with system size. So we argue here that this shows some potential to possibly beat classical simulation in the near future. Now we can't, as you can see with MPS, we can even reach larger system sizes than the experiment. So finally, let me conclude, because I'm a bit over time. So we showed the first large-scale quantum simulation of quench dynamics of lattice gauge theories in 2 spatial dimensions. So I'm a firm believer that 2 spatial dimensions and quench dynamics, there is a really short path towards possible quantum advantage in the future. We also showed the first experimental observation of disorder-free localization. We also have the first experimental realization of quantum parallelism, which actually has a lot of influence on the field of MBL itself. So it's nice to demonstrate it finally on a quantum processor. And as I mentioned, the experimentally accessible evolution times on the Willow chip from Google may challenge state-of-the-art numerical methods in the near future. If we just go to slightly bigger system sizes, we can really start challenging advanced numerical methods. So I just want to mention that I have my synthetic quantum systems group at the Max Planck Institute, but I'm starting a professorship at LMU in October. So let me shamelessly advertise that I have open PhD positions through a starting grant that I got from the European Research Council. So if you love this stuff and you are passionate and motivated about quantum many-body dynamics and quantum simulation, shoot me an email. Thank you very much.